All right, let's take a look at what sort of effect transformations have on our data analyses. Here, what I've done is I'm comparing. Oh, there. I'm sorry. I'm just a little confused. That this was. We've got the same ANOVA here first, but that's not a problem. Or no, I'm sorry. It's one ANOVA. So we've got the mean values here. This is the untransformed. You can see this thing I mentioned called Levine's test. You can see that it's telling us that there's inequality of variances is actually accurate in this case. And we can see our ANOVA and our eta squared value. Now let's take a look at it with the transformed values. One thing to note here is that the transformation, transforming this, we still have a significant Levine's test. In fact, Levine's test told us that the homogeneity of variance was getting worse, when obviously, it was nearly 200 to 1 ratio in the untransformed case. Here's the transformed case, and it's saying it's a worse problem. So again, Levine's test is kind of stunningly bad at times. You can see the p-value here. Notice how we had a non-significant result, and now we have a p-value that's about 8 times bigger. Similarly, the eta squared went from about 0.07 to 0.34. So we can see that there's a real difference between these analyses. Now, one point I do want to make, and this has often gotten lost in the shuffle when I've taught this before, doing transformations and being more in terms of normality does not necessarily mean that your analyses will become significant. What it does mean is that your analyses will become more correct, more in line with what the tests are designed to do, and not applying the tests to situations that are outside of the limits of its capabilities. Same dealio for dad. We can see we do get a significant p-value here, a probability of 0.21. But after we transform the data, we can see our effect size jumps and to more than double as well. So again, we see really, really big differences between the analyses that have used the transformed data versus the untransformed data. Another thing we might do here is we might use the Welch's adjustment and just skip the transformations. I like this approach, but I don't think enough research has been done on the boundaries of this sort of adjustment, because we have a really big issue. Remember the Welch's adjustment, what it does is adjust the degrees of freedom. That's why they're in decimals. The bigger the variance ratios, the more the degrees of freedom are going to drop down from what they would normally be. Normally, this would be like in the 60s or something. All right, and I would kind of did this, but just to compare those analyses again, showing how actually adhering to assumptions really did make a big difference in our results. Now, when you use assumptions, you have to be careful as to what you report. I would always expect somebody to note the sort of transformation they used. Report the F, the P, the eta squared for your transformed data. I would say, though, report means and standard deviations from the untransformed data, just because they make more sense. For example, 937 meters versus 2.17 log transform meters. I do not know if that is the log transformation of meters, but it's hard enough to think in decimal in decimals in the metric system anyway. We're going to log transform something that's metric. It just makes no sense.